Alright, in this video I'm going to introduce you guys to Microsoft Excel's data analysis toolpack hypothesis testing feature. We've just gone through an example in the slides of how to do a hypothesis test if we were to assume that both the standard deviations from each population were known, at which point we could just simply go through the formula like I did in the previous set of slides here. What we've got here, though, is a different example, or excuse me, it's the same example, but we have a different set of data here, where what we have are the actual elicited responses for people indicating which of how much they would be willing to pay at each location for a particular ticket. So we see all of our folks here who are asked about what they would pay to sit in Durham and watch it at Duke, or in Elon and watch this game. As with our last example, what we're going to do is we're actually going to hypothesize that there is no difference in the true means. That is, mu Duke minus mu Elon is equal to 0, and we're going to assess whether or not there's enough difference in the sample averages to be consistent with that view or not. So the way I'm going to do this is I'm going to go to Data and Data Analysis. Once I've got data analysis here, I'm going to scroll to the bottom, and we're going to see a variety of hypothesis test options. Notice here we have one option that says z-tests for sample means. This, again, is assuming we would have knowledge of the population standard deviations, which is a relatively strong assumption to make. So what we're going to do here is we're going to focus on the assumption that we are dealing with two samples with equal variance. Okay, but we're just going to say that we don't know what those variances are, and the formula is going to be given by the one taken from that slide, but all the calculations are going to be done in the background. I'm going to click OK once I've highlighted this, and under variable 1 range, I'm going to select the Duke column. I'm just going to click in cell A1 and use Control-Shift-Down to move on to the next one. For variable range 2, I'm going to select the Elon column. I'm going to select the option that says labels to indicate that the first element of each of these two variable ranges are the names of the populations. And here's where we actually need to indicate what the null hypothesis value is. Okay, so under our null hypothesis, because we assumed mu Duke equals mu Elon, it is equivalent to saying mu Duke minus mu Elon equals 0. So for the hypothesized mean difference, we're going to put 0 there. Again, we can select alpha. With this question, we'll stick with 0.05. And for an output range, I'm going to put this in cell D1. Once we've got that, we can hit OK. And from here, what we can see are both the means for each of the two locations. We have an estimate of the variance for each of the two locations. We have the test statistic, assuming equal variances here, is 6.2. Okay, so I'm just going to highlight this and make it bold. This is our t-stat, and the critical values we're going to compare this to depend on whether or not we're looking for a one-tailed or two-tailed test. Okay? Now, notice that because our hypothesis was a hypothesis of equality, that is, mu Duke minus mu Elon equals 0, this has to be a two-tailed test because we could reject the hypothesis if Duke's average was substantially higher than Elon's, or Elon's average was substantially higher than Duke's. Because this is a two-tailed test, what we need to do then is look at the critical value for a two-tailed test, which I'm going to highlight again. And then we're just going to ask, is my test statistic in the rejection region? That is 6.2 bigger than 1.975 or smaller than minus 1.975? And the answer is, of course, yes, which is going to lead us to reject the null hypothesis, which is going to let us say people are willing to pay more to see the game in Durham than they are in Elon. Another way of evaluating this is to look at what is the P critical two-tail, the P two-tail here, which is actually just a p-value for a two-tailed hypothesis test. So it's going to calculate this for us. If we extend this and show some decimals, we'll see that this is definitely less than our threshold alpha of 0.05, and because of that we can also reject the null hypothesis. Now, one thing we might be interested in doing here is to actually calculate a confidence interval from this table, and so to do this we can break this into a couple of pieces. Point estimate critical value, and standard error. Now our point estimate we can get right from this table, where we can say it's it's x bar Duke minus x bar Elon. For our critical value, again, this comes right out of our table. We can just take the critical two-tail here. So this is going to be equals cell E14. Now the difference here is we don't actually have a way of calculating the standard error very simply. Okay, we could use the complicated formula I indicated on the slides and use these variance estimates right here as S1 squared and S2 squared, and then our values of n for each one of those. Or we can take advantage of the fact that we know that our test statistic, that is t, is equal to PE, our point estimate, minus the hypothesized value under the null hypothesis, which is 0, divided by standard error. Now, what that means is we can take this formula and plug in the fact that H naught is 0, and take T equals PE over SE, and recognize that the one thing we don't have here is SE, because we have the T-stat, we have our point estimate, we just don't have standard error, which means we can solve for that. So the way we can get standard error from this table is we can take our point estimate and divide it by our test statistic. This gives us our standard error, so that if we wanted to come up with a confidence interval, a 95% confidence interval here, we could do it with our point estimate, our critical values, and our standard error, all just from running a hypothesis test on this table.